I am going to go over the combinations, permutations, and probability worksheet I handed out in class. I'll start by just giving you all the answers in case you're just trying to check your results. You don't have to wade through the entire video just to see them, but then I'll go into each problem in some detail. So the correct answers are number 1, 120, number 2, 4, number 3, 1,287, number 4, 39,658,142,160. 5A is 1 out of 4. 5B is 1 out of 13. 5C is 2 out of 13. 5D is 4 out of 13. 5E is 1 out of 52. And 5F is 0. And I just made a mistake. 5B is 1 out of 52, not 1 out of 13. 5B, 1 out of 52. All right. 6 is 3/8. 3 out of 8. 7 is 3 out of 7. 8 is 1 out of 221. 9, it is 2 out of 11. And 10, it is 0. All right, so let's look at these in greater detail. Problem number 1. How many ways can 5 people be seated together at a rectangular table? These are just common counting problems. The ACT always has a few counting problems on there. Say somebody runs a sandwich shop and you have 2 kinds of bread, 3 kinds of meat, and 4 cheeses. How many different types of sandwiches can you make? Well, that's a counting problem. And it all has to do with the number of choices. And here's just the most basic counting problem you can get. Have 5 people seated together at a rectangular table. Well, essentially what it means then is I have 5 seats. So there's 1, 2, 3, 4, 5. I have to put 5 people in 5 seats. So how many choices do I have to assign someone to the first seat? Well, I have 5 people, so I can assign any one of those 5. Now, after I've already seated that person, I only have 4 people to assign to the next seat, 3 people to assign next seat, 2 people, and 1 person. So I multiply all those together, and the total number of ways is going to be that, which is 120. So there's 120 ways to seat 5 people at a rectangular table. Now, it is important that this is a rectangular table. For instance, if I have a rectangular table here, let's say I seat Ann, Bob, Carol, Dan, and Eric. Those seats are unique in a sense because if I move Carol over here, switch places with Eric, then Carol's no longer sitting at the end of the table. Eric is. Carol's sitting over here. So these arrangements is pretty much the same as just having 5 chairs in a row. Now, I want to compare that to what if the table, hey there, hey Willow, over here, go. What if it were a round table? There we go. Okay, so if I'm seating 5 people at a round table, so there's Ann, Bob, Carol, Dan, and Eric. Well, if everybody just gets up and moves 1 seat to their left, that's still the same configuration. Ann, Bob, Carol, Dan, and Eric is the same as Ann, Bob, Carol, Dan, and Eric. And then I could have everybody move again, and that would be the same. And move again, and that would be the same. Move again, and that would be the same. So for each configuration of 5 people sitting around the table, there are 5 ways that is identical. That's just rotating the table or the seats. So with a round table, it's a different consideration. These seats are fairly unique. Round table, that's the whole point behind King Arthur's Round Table, wasn't it? So we need to allow for that. If it were a round table, there's still 120 ways to seat 5 people, but since each group of those 5 seatings can be rearranged 5 ways and not make a difference, we have to divide this by 5. So there are 24 ways to seat 5 people around a circular table. So be mindful of that. Okay, circular table. You can rotate it and get the same result. All right. Number 2. Find the number of 3-letter combinations in the word math. All right. Well, let's consider this. I have M, A, T, and H. All right. Well, looks like I could get M-A-T. That's one 3-letter combination. I could get M-A-H. There's another one. I could do M-T-H. There's a third one. I could do A-T-H. There is a fourth one. So it looks like my answer is going to be 4. But wait a minute. What if I were to draw A-T-M? So let's consider that. Let's look at M-A-T and look at the variations on that. I could have M-T-A. I could have A-T-M and A-M-T. I could have T-M-A and T-A-M. So that one 3-letter combination can be written 6 different ways. So is my answer 4, or is it 6 times 4, which would be 24? Well, the answer is 4, and it's because of that word right there. In math, combinations has a specific meaning. We have 2 terms to throw about here, combinations, and the other one would be permutations. With combinations, order doesn't matter. That means MAT is the same as MTA, ATM, AMT, TMA, and TAM. Those are all considered the same 3-letter combination. The order that they're in is immaterial. With the permutation, order would matter. All these would be considered distinct. So if the question is find the number of 3-letter permutations, the answer would be 24. Since it's combinations, the answer is only 4. Now, this is all pretty easy just to write out if I just have a 4-letter word here to choose from. But what if the word were like refrigerator? Then it gets a little more difficult. So there must be some formula that will help us calculate combinations and permutations. And indeed there is. Okay. From the last problem, we saw that we multiplied 5 times 4 times 3 times 2 times 1. Anytime we take a number, let's say 6, and we multiply it by all the numbers successively less than itself, 5, 4, 3, 2, 1, that has a that is a mathematical function. It's called factorial, and it's usually written with an exclamation point. So 6 factorial would be 6, 5, 4, 3, 2, and 1. And what would that be? That would be 720. Okay, and on your calculator, this is normally written as n factorial or x factorial. If you have a scientific calculator, you almost certainly have a button. There's mine right there, x factorial. Okay, so we have a formula for combinations, and it is written this way. Combinations, n, r. Okay? And it would be n factorial over r factorial times n minus r factorial. And this would be, normally this is said n choose r, because what we're saying is how many ways are there for me to choose r items from n items? How many ways are there for me to use 3 letters from 4 letters? Well, n choose r. So to do this problem, we would say that that is going to be C 3 choose, or 4 choose 3. 4 choose 3. I have 4 letters. I need to choose 3 from those 4. And according to our formula then, that would be 4 factorial over 3 factorial times 4 minus 3, which is 1 factorial. 1 factorial is just 1. 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. So that means the 3 times 2 times 1 is going to cancel out top and bottom. We'll only be left with a 4. Answer 4, which is what we already know by writing it out. Okay? Permutations on this same problem. The formula is n factorial over n minus r factorial. So here we choose 4, permutate 3. We'd have 4 factorial over 4 minus 3 factorial. 4 minus 3 factorial is 1 factorial, which is 1. So it's 4 factorial, which is 4 times 3 times 2 times 1, which is 24, again, which we already figured out if these were unique. But combinations implies that those are not unique. Order does not matter. So the correct answer to this problem is 4. All right. Look at 3. All right. How many ways can a 5-card hand of diamonds be dealt from a standard deck of 52 cards? I wonder. Well, here we have 5 cards we need to deal out. So I look at this and I have 52 cards, and I know that there are only 13 diamonds in a deck of 52 cards. And that is that type of daily information is something that you'd be expected to know on the test. So I only have 13 diamonds to choose from. So that means to deal this first card, if I has to be a diamond, I only have 13 choices. That means for my next card, I only have 12 choices. Then 11 choices, 10 choices, and 9 choices. Dink, 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 dink. All right. So, the question is, does order matter? Is this considered a different deal if I deal ace, 10, king, queen, jack, or if I deal 10, jack, queen, king, ace? Are those two hands different? No, they're not. So order doesn't matter. This is another example of a combination. So that means for every 5-card hand I have to divide that by 5 factorial, because I can rearrange those cards 5 factorial ways and still have the same configuration of 5 cards. Okay? So this is another example of a combination. I have 13 diamonds. I want to choose 5 cards from those 13 diamonds. So according to our formula, this should be 13 factorial over 5 factorial times 13 minus 5 factorial, which is 13 factorial, that's a ginormous number, divided by 5 factorial, which I know is 120, and divided by 8 factorial, 40,320, 1,287 ways to deal a hand of 5 diamonds from a deck of 52 cards. It's only 13 diamonds to choose from, so 13 choose 5. 1,287. Okay, there we go. Number 4. Oh, here we go. A club with 42 members wants to elect a president, a vice president, and a treasurer. From the remaining members, an advisory committee of 5 people is to be selected. How many ways can this be done? You don't say. Well, let's start with the first thing here. We have 42 members. We need a president, a vice president, and a treasurer. Now, let's say I pick Larry, Moe, and Curly. Well, if I then choose Curly, Larry, and Mo, even though they're the same three people, that's a different combination because of the assigned duties. If Mo is president rather than treasurer, even if Curly and Larry, it's still the same group of people, but it's a different consideration. So this is not a combination. Order matters here. This is a permutation. And if we just look at it this way, I have 42 people to choose from. So that means my first spot, I have 42 people I can pick from. After I've chosen a president, I only have 41 people I can pick from, and then 40 people I can pick from here. So that should be 42 times 41 times 40. 42 times 41 times 40, which equals 68,880. Now, I don't have to consider either that I'm going to have combinations here because of the assigned roles, all of those are unique. Even if I have the same three people, if they're occupying different roles, that's considered a different count. So this is a permutation. And if you were going to write this out formally, you would say 42 P3, which would be 42 factorial divided by 42 minus 3 factorial, which is 39 factorial. That means everything from 39 on down is going to cancel out, and we're left with 42 times 41 times 40. So that's that. Okay. So that's how to select the vice president, president, and treasurer. Now, to get the 5-member advisory committee, well, I have 5 slots here. But now, if I have Larry, Mo, Curly, Shemp, and Curly Joe, order doesn't matter here. Those same 5 people, depending on which order I pick them, are still the same 5 people. It doesn't matter if I choose Mo first or Curly first. If I choose Shemp second or Larry second. As long as I have the same 5 people, it's the same deal. This is an example of a combination. This would be, well, I've used up 3 members by choosing my president, vice president, so I only have 39 people left. So 39 choose 5. So this is going to be 39 factorial divided by 5 factorial divided by 39 minus 5 factorial, which is 34 factorial. Right? That means everything from 34 on down cancels out. 5, blah, 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 blah. So I'm going to take 39 factorial, a huge number, divided by 5 factorial, which I know is 120, divided by 34 factorial. Oh, look at that. There are 575,757 ways to choose 5 committee members. Because here, order matters. Here, order doesn't matter. So the end result would be the total number of ways I can choose these 3 times the number of ways I can choose these 5. So I need to now multiply these 2 together. And if I do that, 575,757 times 68880 equals 39658142160. And there you go. There's your answer right there. So this problem uses permutations and combinations. All right, probability. Suppose a single card is selected from an ordinary deck of cards. What is the probability that it's whatever? Now, probabilities are just the consideration of the number of ways a specific event can happen divided by the number of ways all the events can happen. So the probability that is a heart. Well, the probability that it's a heart is equal to the number of ways I can draw a heart divided by the ways I can draw any card. Well, drawing any card, we know that. That's just 52. I have 52 deck cards in a deck. Now, the number of ways you can draw a heart, well, how many hearts are in the deck? Well, there's 13. So the probability that it's a heart is going to be 13 out of 52, or 1 out of 4. And there you go. That's all there's probability. What's the probability that it is an ace? So the probability that I'm going to draw an ace, well, the total number of ways to draw a card is 52, but how many aces are in the deck? There's only 4. So the chance of drawing an ace is 4 out of 52, or 1 out of 13. What is the probability that is a 2 or a king? You need to be very careful when you're talking about math, whether they're using the word or and, because it makes a huge difference often. So let's look at this first one here, or. So it's a 2 or a king. Right? Well, the number of ways I can draw a card doesn't change. It's still 52. But how many different ways are there for me to draw 2 or a king? Well, there's 4 2s and 4 kings for a grand total of 8. So 8 out of 52 ways to draw. I can reduce that to 2 out of 13. So the probability of drawing a 2 or a king is 2 out of 13. Right? What is the probability that it is a 2 or a heart? Probability 2 or a heart. Well, again, there's only 52 ways I can draw any card, so that stays the same. But now probably 2 or a heart. Well, I know that I have 4 2s and 13 hearts, which is 17. But one of those 2s is a heart. So if I use 17, I'm counting that 2 of hearts twice. I'm counting it both as a 2 and as a heart. So there are not 17 ways to choose a 2 or a heart. There are 16 ways to choose a 2 or a heart. 16 divided by 52 is 4 out of 13. What is the probability that it is a 2 and a heart? So the probability of a 2 and a heart. Well, there's still 52 ways to draw any card. But there's only one way to draw a 2 and a heart, because there's only one 2 of hearts in the deck. So if the cards are going to be both a 2 and a heart, there's only 1 out of 52 ways that can happen. Okay. What is the probability that it is a 2 and a king? So the probability that it is 2 and a king. Still 52 ways to draw a deck of cards, but last time I checked, there was no card in the deck that is both a 2 and a king. So it's 0 out of 52, or simply 0. And there you go. Suppose a Chant family wanted to have 4 children. What is the probability of having 2 boys and 2 girls? You know, these problems that involve having kids can be just, for something so simple, you figure, well, I got 2 choices, boy or girl. It can get very complicated. But let's look at this example right here. We have 4 children. So again, probabilities, the number of ways a specific event can happen, divided by the number of ways any event can happen. So we need to first figure out how many ways are there to simply have 4 children. Okay? Well, let's figure it out. I have child number 1, 2, 3, and 4. Well, I have 2 choices for the first child. It's either boy or girl. I have 2 choices for the second child. It's either boy or girl. I have 2 choices for the third child. Either boy or girl. I have 2 choices for the fourth child. It's either boy or girl. Ding, ding, ding. So that's 2 times 2 times 2 times 2. There are 16 ways to have 4 children. All right. So I know my probability is going to be something over 16. The trick now is to figure out how many different ways there are to have 2 boys and 2 girls. Now, we could write this out. Thought about it. We know we have boy, boy, girl, girl. We could have boy, girl, boy, girl. We could have girl, boy, a boy. We could have a girl, girl, boy, a boy. We could have, let's see. Oh, no, girl, boy, I got that one. Oh, we could have girl, boy, boy, girl. We could have boy, girl, girl, boy. So it would seem that there are 6 ways to have 2 boys and 2 girls. So the answer is going to be 6 out of 16, which is 3 out of 8. But wait a minute. What about, do I have time to write all this out? Is there some way that I can figure out how many ways there's to have 2 boys and 2 girls? Well, yes, there is. Because I have 4 slots. So there's 4 factorial ways for me to arrange those slots. Let's say I have A, B, C, and D in there. Not boy and girl yet. Deal with that in a second. There's 4 factorial ways for me to arrange those. I can put the one here, the second one there, the second one there, 4 factorial ways. So there's 4 factorial ways for me to fill up 4 slots. Now, if I'm just filling up with boy, boy, and girl, girl, that means everywhere there's a boy, I can just swap it with the other boy, and it's still the same thing. If I have boy, girl, and I swap those 2 boys, I still have boy, girl, boy, girl. If I swap those 2 girls, I still have boy, girl, boy, girl. So even though there's 4 factorial ways to do that, each way is going to contain 2 boys that can be swapped and still be the same, and 2 girls that can be swapped and still be the same. So how many ways are there for me to swap 2 boys? Well, there's 2, or if you want to be technical, there's 2 factorial, which is 2 times 1, which is 2. But I want to be, totally math here. So the number of ways to choose 2 boys, to count 2 boys and 2 girls in 4 children is 4 factorial divided by 2 factorial divided by 2 factorial, which is going to be 4 times 3 times 2 times 1, which is 6, or which is 12, divided by, no, that's 24, divided by 4. 6, yeah, which we already knew, 6. So 6 out of 16 ways, or 3 out of 8. Okay. Whew. What is the probability of a family of 3 children containing exactly 2 girls, given that at least one of them is a girl? Oh my gosh, what do you mean? Well, let's start with what we can figure out easily. 3 children. How many ways are there to have 3 kids? 1, 2, 3. Well, I can have a boy or girl, a boy or girl, a boy or girl. So there's 8 ways to have 3 children. So I know my probability is going to be something over 8. Or is it? Because look at this last provision here. Given that at least one of them is a girl. Wait a minute. What does that mean? Well, if I write out all the choices for having 3 children, I could have boy, girl, girl, boy, boy, girl, girl, boy, girl, 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 boy, blah, 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 blah. Is there any case where at least one of them is not a girl? Yes, there is. What if I had boy, boy, boy? Yeah, that is not a consideration here because it's a condition placed in here that at least one of them is a girl. So that means there are not 8 ways. Because of that condition, I have to disregard this one. So there's only 7 ways total that satisfy these conditions. Now, how many of those ways contain exactly 2 girls? Right. Excuse me. This is easy if you just write it out, but we can view it as a combination. There are 3, choose 2 ways, because 2 girls, I just want to pick 2, just which is 3 ways to have exactly 2 girls and 1 boy. So my answer should be 3 out of 7. And with this number this small, you can almost just as quickly write it out too, because you know that there can be boy, girl, 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 boy, and girl, and girl, girl, boy. There's no other option that has 2 girls and 2 boys. So 3 out of 7. All right. Number 8. Two cards are drawn from a standard deck of 52 cards. What is the probability the second card is an ace if the first card was an ace? All right. So I'm just going to deal out 2 cards. One's going to be an ace. The next one's going to be an ace. What's the probability that that card is an ace if I've already dealt 1 ace? Well, let's figure it out. Probability of ace if ace. Oh, okay, so the probability that I'll draw an ace, we already looked at that. We know that is going to be 4 out of 52. Now I'm going to multiply that by the probability of whatever the second card is. If I also want the second card to be an ace, I look at how many aces I have left. I've already drawn 1, so I only have 3 aces left in the deck. Similarly, I only have 51 cards left in the deck. So that's going to be 3 out of 51. With conditional probabilities like that, I multiply them to get the final probability. So that's going to be 4 divided by 52 times 3 divided by 51, which is a big decimal. I'm not going to do that. I'm going to say that is 12 out of 2,652, or 1 out of 221. And there we go. You know. All right, number 9, number 9, number 9, number 9. If you roll and sum a pair of dice, what is the probability of rolling a 3 given that one die came up 2? All right, well, let's just look at the number of total ways we can roll dice if one of them has to be a 2. Okay, I could have a 1 and a 2. I could have a 2 and a 2. I could have a 3 and a 2. I could have a 4 and a 2. I could have a 5 and a 2. I could have a 6 and a 2. But similarly, I could also roll a 2 and a 1. And a 2 and a 3. And a 2 and a 4. And a 2 and a 5, and a 2 and a 6. Can't count the 2 twice, it's the same thing. So that means there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 ways to roll 2 dice if one of them has to be a 2. Now, of those 11 ways, you can see there are only 2 that actually give us 3. So there's your answer right there. 2 out of 11. Ta-da! All right. Number 10. If you roll in some of pair of dice, what is it probably rolling a 2, given that one die came up a 2? Okay. Well, I could go ahead and write out all those options again of how many different ways there are to roll 2 dice if one die is a 2, but the only way on dice that you can get a 2 is if you have snake eyes. And we can't roll snake eyes if one of the dice has to be a 2, so the answer is 0. There's no way that can happen. All right, there we go. Thank you very much. If you have any questions or if you caught any errors or something, do let me know. Get that taken care of. Thanks very much.